Okay, so now come to the moving coil galvanometer. In short, it is also known as MCG. So, what is the purpose of this instrument? So, this is the very fundamental instrument, and this can detect very small amount of current, as well as with the help of this instrument we can measure also very small current. So, we can say it is a fundamental electrical device which is used to detect as well as measure very small current. It could be in the range of, we can say, range of milliampere or microampere. It can be used to detect current in the range of milliampere as well as microampere. See the construction diagram. And one more thing here, what is the principle of this? It works on the principle of torque on current carrying loop in magnetic field. Okay. It works on the principle of torque on current carrying loop in magnetic field. To see how it works and what is the construction diagram of this. See the construction. Construction of moving coil galvanometer. So, in this moving coil galvanometer, we are having a small cylindrical soft iron core, and on this core wire has been wrapped like this at the middle of the core. This is called your soft iron cylindrical core, and on this the wire has been wrapped. Here this is suspension wire with the help of a spring. So, one end of the wire is this, that we can say terminal T1. Another end of the wire, that can be set terminal T2, and here this is your 0, and this can be set as a maximum current in IF, and this is the pointer, and this kept in a between the two horseshoe type of poles of magnet. This is your north pole, this is your south pole, and horseshoe pole of the magnet produces radial magnetic field like this. So, T1 and T2, this is soft iron core, and this we can say suspension wire. T1 and T2 are terminal of MCG. Terminal of MCG, and this is your scale. If we are looking from the top view, this is your, you can say, front view. This is the front view, and when we are looking from the top it will appear like this. This is your north pole, south pole, and these are the coils, magnetic lines of forces, like this, and this is your pointer here. This we can say magnetic poles, and this is your soft iron core, and this is a wire wrap or coil, we can say. This is a coil, and this view is the top view. So this is the construction of your this. So here we can say in the construction, in a cylindrical soft iron core, wire has been wrapped, wire has been wound. It appears a coil is kept between the poles of a magnet, between the poles of magnet, and this core is your, so this core is suspended with a suspension wire, is suspended with a suspension wire, made from phosphor bronze material, this. So this is the general construction diagram of a galvanometer or moving coil galvanometer. Now working of a galvanometer, how it works. Now working of MCG, moving coil galvanometer. See, so galvanometer is always connected in series with the branch across which current has to detect or measure. The first point, galvanometer has to be connected in series with the branch in which current has to measure, current has to detect or measure. So first of all, we should connect a galvanometer with a branch in which current has to measure in series. Now as soon as current starts, it means these are the terminals. So if we are making a diagram in the rough diagram, so this is the G for galvanometer, and these are can be said as a terminal T1 and T2. So from one of the terminal current your enter, and from other it will leave like this. So when current enter from one of the terminal here, it passes through the wire which has been wrapped over a cylindrical core. So when the current is going through these wire, it means these wire just like a loop, and then this loop is kept in a magnetic field. So when current passes through the wire which has been wrapped over a cylindrical core, passes through the wire which has been wrapped over a cylindrical core, So these current carrying wire act just like a current carrying loop. So these current carrying wire act as a current carrying loop, kept in magnetic field. So now, as already we have read, whenever current carrying loop kept in magnetic field, so it experiences a magnetic force as well as magnetic torque. So this current carrying loop experience magnetic torque which is given as torque is equal to m cross b. So magnitude of torque, if I am talking about, mb sin theta, m is the into b sin theta. This is the torque experienced by current carrying loop, where n is the number of turns in the loop, I is current, S is the area. Where n is the number of turns on the loop, S is area of loop, and theta is angle between magnetic moment and magnetic field. Magnetic moment and magnetic field. So this is the torque acting on this current carrying loop when it is kept between the poles of a magnet. Now, to making maximum torque or making torque independent of theta, for making torque independent of angle, independent of angle theta, we are using concave shaped poles of a magnet. we are using concave shaped poles of a magnet which produces radial electric field magnetic field, radial magnetic field. It means this field, whatever the field we are getting here like this, we can say it is your radial magnetic field. So, because of radial magnetic field, and since our conductor has been wrapped near to the center of the core, so because of radial magnetic field and the coil and the wire and radial magnetic field, because of the radial magnetic field and the wire has been wrapped near to axis of cylindrical core, and wire has been wrapped near to axis of cylindrical core, the theta is almost 90 degree. So, the coil experience maximum torque. The torque maximum will be here NIS into B. So, this is the maximum torque experienced by this coil. Because of this torque, the cylindrical core rotates. Now, so what is the meaning of that? As soon as torque start acting on this coil, so this core starts rotating. Due to rotation of core, there is a twist develop on the suspension wire. Due to rotation of core, twist develop on suspension wire, which opposes the rotation of core, opposes the rotation of core at equilibrium. Both torque balance each other, and the pointer will give certain deflection, and the pointer gives deflection. So, at equilibrium, magnetic torque is equal to torsional torque. So at equilibrium, magnetic torque is equal to torsional torque. So magnetic torque is this, NISB is equal to C into phi. This is the condition. So I written as C by NSB into phi. This is the condition for current, where C is the torsional constant of suspension wire, torsional constant of suspension wire while phi is deflection in a pointer. Deflection in pointer or amount of twist developed in suspension wire, or amount of twist in suspension wire. So this is the condition here. Then current further, I is written as here K into phi, where K is equal to C by NSB, and it is called torque galvanometer constant. K is called galvanometer constant. So in this manner we can have, so this is the general idea about the working of a galvanometer. So here I is proportional to your phi and K depends on your torsional constant, number of turns, S is the area of the coil, B is magnetic field. So now this whole, you can say, construction is kept inside a box, just like this is a box, and it is called as a galvanometer. So symbolic representation of galvanometer is this, and inside this which type of diagram is there or what type of construction is there, this is represented by here T1 and T2 are the terminal. So some term we can write like this. So as I is equal to C by NSB into phi, or we can say I is equal to K into phi, where K is a galvanometer constant. So now here, this is the symbolic representation of galvanometer. Symbolic representation of galvanometer. Now for the meaning of G, G also called your galvanometer resistance. Galvanometer resistance. So meaning of galvanometer resistance is this, this wire which has been wrapped over a cylindrical core, this wire must have some resistance. So whatever the value of that resistance, that is called G. So it is the resistance of wire which has been wrapped over a core, and IF is a Normally in the pointer we are showing IF. IF is also known as a full scale deflection current. Full scale deflection current means it is the maximum current. It is the maximum current a galvanometer can have. A galvanometer can have. This is called your full scale deflection current. Now certain terms related to galvanometer. The first is a current sensitivity. Current sensitivity in short it is written as current sensitivity. The meaning of sensitivity means how the galvanometer can be sensitive about the current, means it means how a small current can show certain deflection. The current sensitivity C is written as deflection per unit current. So deflection per unit current, or we can say phi by I. So phi by I is nothing, it is the reciprocal of galvanometer constant. So C as further written as reciprocal of galvanometer constant, and this is your nothing NSB by, so K is a, so we can write here CS is reciprocal of galvanometer constant. Galvanometer constant. So as the sensitivity means as small current it shows a deflection. It means how the galvanometer can show very small current also. So it depends. The sensitivity of galvanometer and current sensitivity of galvanometer depends on number of turns, area of the turn, and inversely proportional to your galvanometer wire constant. C is the torsional constant of the wire. It means if the torsional constant is less, so it give more deflection or sensitivity of the instrument will increases. Similarly, we are having voltage sensitivity. The sensitivity can be increased by decreasing the torsional constant of the wire, as well as it can be increased by increasing the number of turns, increasing the magnetic field, as well as by increasing the area of the coil. Similarly, voltage sensitivity. Voltage sensitivity Vs. It is defined as the potential drop. It is defined as the deflection per unit potential difference across galvanometer. So voltage sensitivity means here phi by V and phi by I into R. In place of R we can write G, because G is taken as galvanometer resistance, and phi by I already we have found here, the 1 by K into G. This is your voltage sensitivity, where K is galvanometer constant, meter constant, and G is resistance of galvanometer, resistance of galvanometer. So this is the basic idea about moving coil galvanometer. Now see one or two example based on the galvanometer. Now see, this is one of the example. A galvanometer having 30 division has current sensitivity of 20 microampere per division. To find the maximum current it can measure. So it means in a scale we are having total 30 division. It is given in the question here, and it is also given the current sensitivity. It means each division can measure how much current? 20 microampere. And since each division can measure 20 microampere, so, and we want to calculate maximum current it can measure, so maximum current will be from all the 30 division. So we can write as current sensitivity, see, as the current sensitivity CS is equal to deflection per unit current. So now if we want to calculate total current here, and total current will be your total deflection. So see here. So total current I, total current is equal to number of division into current measure per division. Current measure per division. So number of division here 30 and current measure per division here 20 microampere. So this will be your 600 microampere. So total current or maximum current. So maximum current, or we can say here maximum current is equal to 600 microampere or 0.6 milliampere, directly we can say. Now see another example, example number 2. So this is another example. In this example, a rectangular coil of area 5 into 10 power minus 4 meter square and 60 tons. So this coil is in a radial horizontal field of this Tesla, 9 to the power minus 3 Tesla. So what is the torsional constant of suspension wire if current of 2 ampere produces deflection 180 degree? It means the question is like this, okay, this is our, if we have recall the diagram of your galvanometer, moving coil galvanometer, and here current your 2 ampere. Because of that this wire had torsional constant you have to calculate. So as we know, in equilibrium magnetic torque is equal to your torsional torque. So magnetic torque, if we have remember NISB, torsional torque is your C into phi. So we have to calculate the value of C. The C can be written as NISB by phi. So this we can write here. N, number of turns 60. How much current is flowing in this? 2 ampere into 2. S is the area of the loop, which is 5 into 10 power minus 4. And magnetic field is given 9 into 10 power minus 3 Tesla by phi. Phi your 180, directly you can write in the degree 180. Now see from this 60 into 3, this your 180 cancel. So now how much left here? 5 into 2, 10, 10 minus 1 minus this is 3 into 10 to the power minus 6. So this is the, you can say C value. The C is written as here torque. Torque means here this is your Newton meter per degree. This is the value of torsional constant. The C is 10 to the power minus 6 Newton meter per degree.